that good light, or should we try to change it? Good.
I have a question. Will the slides be uploaded before, like,
Before the lecture, you mean before?
yeah, so that we can take notes?
Yeah, we can try. I have to coordinate with Eric. I mean, I had them uploaded on our thing, but I can ask. We can ask him to post. Okay. I think we're going to get started and let people trickle in. So today we're going to finish up the variability and also start a little bit on the memory, in particular SRAM. And there will be a lecture on Thursday, guest lecture by Apple, talks a little bit more in depth about some of the advanced SRAM design techniques. So you'll hear a little bit from the industry. I kind of put this news from TSMC. It varies every week. One week is low yields, the next week is high yields. So we'll see what actually happens. But needless to say, both Intel and TSMC are kind of in the race to get to the 3 nanometer technology in the next few years. And the interesting thing that we'll talk about or continue talking about today in the lecture is, what does the yield mean, right? Yield could be per device, per some metal feature, per some process feature, or could be for a whole big design. And what you'll see is that what these foundries do is they actually run it at all of these levels. Like, for example, Intel would design a processor, an early version, and run it through the early versions of the process to actually tune the process to the design. And we'll see today in the lecture, there are some system level consequences of these lower level transistor interconnect and gate yields that you have to pay attention as a designer. Before we dive there, just a few announcements. And midterm report is due this week, so it should be 4 pages, like conference format, like you reviewed the state of the art, this is what you're proposing to do. And it would be good to include a little timeline so that you have kind of, let's say, a work plan, like by week, what are you trying to accomplish, how you plan to test your design, what do you plan to measure. That will be kind of your, like, measurement section. You don't have it yet, but like a plan for that will guide you how to structure your design, how to structure your test benches, and be able to converge faster. We're also going to post assignment number 2 this week. Will be due after the break. And we'll focus mostly on the material in the, like, since assignment 1, so past the system interconnect, all the modeling, transistor models, things like that. Okay, we're going to talk a little bit about the impact of variability, kind of in a larger sense first. What that means is, for critical paths, for the whole design, right? You no longer have a single gate that you have to, or transistor that you have to worry about and its threshold variations, but it's actually something that spans a whole chip, right? And let's say digital, this is a digital design class. So you go out there and you want to design an ASIC, let's say you're a design lead, this is the first thing you're going to have to start worrying about. Because you can't just write RTL, you can't just run place and route tools. What you first need to do is set the design methodology. And remember, in your labs, when you're running even synthesis, but also even more importantly, place and route, you have these clock constraints that you need to set. And there are certain things that are like uncertainty that you can dial in as a variable. So the tool can try to deal with that uncertainty in terms of the delays that it's trying to estimate for both hold time and setup time violations on the paths, right? So how do you set up that uncertainty parameter, right? You could be super conservative and set it up to be a really large. Well, that will lower your clock frequency. So whatever gains you're trying to get at, let's say, the architectural level may be completely eaten by that conservatism, right? If, however, you're too aggressive, so you make that uncertainty factor very small, then of course your yield is going to be low because a lot of your chips are not going to work, because that uncertainty factor does not include just, let's say, the power supply noise in the chip or thermal noise that adds to your jitter, right? Which you will always have, but it also includes a lot of this variability at the gate level, at the critical path level, at a whole block level. That is somewhat systematic, somewhat random, die to die within die, lot to lot, right? So you have to somehow have a way of estimating kind of what's the golden number, right, to put in there. And that will depend on how your design is structured. So some of this stuff that we're teaching you in the previous lecture and this lecture can help you do that. But it's actually a pretty sophisticated process. And actually every company has their own secret sauce about how do they go about estimating these things. Especially it is the case that you never start a chip in a process that's already super stable, because then you're too late compared to your competition. So what you're starting is in something that's, let's say, a 0.1, 0.5 PDK, where the models you're dealing with, the fab is just running the first things through, and you still want to start your design with these, because by the time the fab cycle, about 2 years to ramp up a new process, that's how much time you need also to design a really big system on chip. So you're kind of trailing that process and improving your design and design methodology and predictions as the fab is basically maturing the process. So you can be one of the first to tape out in that new process and have a new design in a new process, right? It's kind of like a double win. So that's why it's important to kind of understand these fundamentals so that you're able to help establish the design methodology. That usually happens with the fab. So trying to understand their statistics, what they're telling you about the process. You're trying to back correlate that with what your design looks like and how applicable those statistics and in what places are to your design. And then you keep iterating on that, right? So we're going to go through some of these effects. Some of them are easy to understand, some of them are harder, but it's basically a design methodology. So the first thing you worry about is a critical path, right? You have a source flip-flop or register, you have a destination register, you have some end stages of logic, right? And you would go and calculate what is the clock, nominal clock at which this system will run. Okay, you have clock to Q delay here, you have setup time here, you have the nominal gate delay of every stage. You can add some clock skew between these two registers. And that's kind of the end of the determinism, right? Now you have to start adding the uncertainties, right? There will be some jitter on this clock. There will be some power supply noise that's added to both the gates. So there will be some uncertainty in the delays. And then there will be statistical variation in that delay. Is the delay D1 correlated with D2, or is it uncorrelated, right? So if all the delays are correlated, right, my total critical path delay is a sum of these, right? So if they're correlated means if one is longer, the other one is longer too, right? When I sum them all up, they're all gonna get just much longer, right? However, if one is longer, the other one is shorter, another one is longer, another one is shorter, when I sum them up, they're basically averaging out, right? So if you look at this critical path statistically, right? If every delay here is a nominal delay plus some random variation, right? The total critical path is sum of the nominal delays plus sum of all the random variations. If these random variations are uncorrelated, right? The total power of that random variable is going to be n times the randomness of each stage. I'm talking about power. So when you take the sigma, it will be 1 over n, right? Because you have, or square root of n, because you're dividing kind of per effective per gate. What does that mean? So for the total critical path, your uncertainty increases because you have n stages, each one had some uncertainty. But compared to the critical path delay, which is now n times the nominal gate delay, you're like a square root of n less, right? So that's what basically this curve shows, right? It's the sigma over the mean of total delay. And as you increase the number of stages, you're basically reducing your normalized variance, sigma, by a square root. Does that make sense? I'm not going to write the formulas, but I hope people kind of get it, right? However, if every delay is totally correlated, every variation to the next one, then you increase the number of stages. Well, nothing changes. Every gate, let's say, got X% worse compared to its own delay. Okay, the total delta is n times X%, but you're dividing it by n, which is the number of stages. So it's still X% of the total, right? And that's why basically this red line for totally correlated stuff, you don't get a change. So which one of these is better? If you're trying to squeeze the cycle time to be as aggressive as possible, which one gives you better yield?
Non-correlated?
Yeah, so non-correlated means all statistical, right? You will still get some variation. You have to set your clock cycle somewhere, and then the cumulative distribution function up until that time, right, will give you some yield maybe 90% or 99%, whatever your cost tuning and gross margins of the product, and all these calculations have to come into play when you're designing this methodology. But that's basically one of the nice consequences. Another one is kind of the opposite. So you look at one path and you make some conclusions. Then you look at k paths, right? And what happens here is a little bit harder to understand. I'll try to explain it how it goes. If we had completely two paths which are uncorrelated. So if we look at one path, basically it will have some mean and some variance, just like we did on the previous slide, right? Whatever the gates are correlated within or uncorrelated, there will be some mean and some variance for path one, right? That gives you some distribution function of delay, arrival at this flip-flop. That's a probability, a function of time and probability, right? Now, if you add one more path, that path has its own distribution function for arrival times. if my goal is to have 50% yield, right? On one path, where should I put my clock cycle time? I still have one path. Any guesses? I want 50% yield on one path. Where do I put my cycle time? It's a normal distribution, right? You have some random process that is added to nominal path value, right? So that process is zero mean, right? And has a Gaussian shape, you're adding it to the nominal path value. How should you set up your clock time so that your yield is 50%? Meaning you fail 50% of the time, you pass 50% of the time. Any idea?
Nominal path.
Yeah, nominal path, the mean, right? Because the left side, when you integrate, okay. I mean, you have some nominal delay, and now you have the Gaussian sitting on top. So if your clock registers here, right? This is the launch clock, this is the on, this is your clock cycle time, right? Then, okay, for this time, you're gonna be good. But for this time, you're basically going to have a setup violation. Right? So your yield is gonna go down. Your chip is not going to work. So you have to relax the clock time to be able to catch these variabilities. And you can do that. If it's cold, you basically, it doesn't work at all. So, okay, what happens if I have now two paths? Right? I have this path, and I have another path that has the same thing, right? But I want both paths to work. So if I set my cycle time to T nom, what's the yield?
Quarter.
A quarter, okay? Because it's 0.5 here times 0.5 here. So the yield is 0.5 squared, right? So where should I set my boundary or my clock cycle so that I have 50% yield? Yeah, it should be root like 0.7-ish, right? So let's say 1 sigma away here, right? And now I need this to be 0.7, whatever, 5-ish, right? So that together, they give me 50%. Well, if I have 3, it's even worse, right? 1,000, 10,000. Okay, so that's what these curves are showing. The more paths you have, as you're doing your CDF, which is cumulative distribution function, that's this integral of the normal, to the power, right? Your distribution, your CDF kind of starts like this, and then it basically goes and becomes very sharp and shifted to the right. And you can kind of run the statistics to see that this paper has a really good analysis of that across the paths. And of course, you can dial in the correlation coefficient, right? This is a story about completely uncorrelated paths, because remember, I was doing to the power of. That's only if paths are uncorrelated, right? So you would have this to the power of whatever, k in our example, right? But if the paths are correlated, if these two paths are fully correlated, right? And I have I'm here at 50%, what happens with the yield? If these are, yeah, these are two Gaussian distributions, but they're fully correlated. Whatever happens here happens here. Then for T nominal, what's the yield? 50%, right? So then I don't need to shift my clock cycle, right? The distribution is going to be wider, right? But the mean is going to be actually closer to the more aggressive side, right? So those are some things to really think about. And as we go through and look at the various kinds of variations that we have, you'll see that it's not just randomness like random dopant fluctuations. It has to do a lot with layout. Where are your gates with respect to each other? What's the density around each one of the gates? So some mining of the data of your place and routed design, carrying floor planning, how the standard cells are designed, all of that plays a role, right? So it's actually a pretty complex problem, but people get paid big bucks to solve it, right? Okay. So we're going to talk a little bit about process corners as one of the things that comes into play in all of this. There are certain processing steps as to how you form the transistor as well as interconnect. And all of them have some inherent variability in there, right? That can affect the whole wafer and actually the whole lot. It also can be different lot to lot, just depending on circumstances in the foundry, the humidity level. All these things are very precisely controlled, but nevertheless, there's always variation, okay? There's a Intel, when they build the fabs, they replicate everything in the fab. The fab is built, and for a while back, tens of years, a decade ago or more, they had a yield issue in the new fab that basically they couldn't figure out. Turned out the only difference was the paint on the wall. And the paint was outgassing differently than in the other fab. And that outgassing was, even though it's clean room and everything is basically supposed to be filtered out, that small percentage of outgassing was affecting the equipment. So you got to be very super paranoid about everything when you're trying to replicate the process and also make some advancements to it. Okay, so we're going to talk about some of these things as to how it applies both to planar technology and then also to FinFETs, which are more modern. So to make an integrated circuit, you have to go through a set of mask lithography steps, as we've covered already in the lectures. But each one of these steps, for example, this is showing the gate etch, right, where you apply the resist, you have the mask, try to pattern the resist, you then develop the resist. So the things that were basically in the shade, depending on the type of resist, this is positive resist, there's also negative resist. Some things will remain, whether they were exposed or not. And then they present basically a mask, a hard mask for the etch step to be able to etch the material that's not under that hard mask. And so you will get essentially, let's say these are gate pitches, right, in the picture. Now, as this process is going, all sorts of variables can affect it. The light intensity may basically, there's a certain profile, how it illuminates the resist and how rough the resist ends up being, like, meaning these sides. What's the variation in width here and the width and the overall width? When the etch starts happening, also how uniformly are you going down? What's the roughness of that surface? What's the kind of cavitation of that surface? That also depends on how many of these are and how closely they are spaced. Because the more closely things are spaced, the etch material will basically kind of have to work harder. Whereas somewhere else where they're not as closely spaced, you know, it has basically more stuff to eat. So it will basically have to be slowed down. And so you may end up having situations where there's big spacing, it progresses faster or slower, and then here only partially aches the little trench, right? Or vice versa, depending on the type of etchant material. So these are these microscopic loading effects where your thing is never going to come out as perfect as you would want it. And these local variations will be very much pattern dependent. And what is a pattern? Well, that's your layout, right? So depending how you want to design a cell, and cell to cell, like NAND gate to NOR gate to AND or invert, like all these layouts could be different and slightly impact what's happening in the delays. So these are some older experiments, but just to illustrate the point that people are really worried about these things. So you have 90 nanometer, 45, these are all planar structures. So, okay, you have a single gate inverter layout, then you try to basically put dummy poly to solve these loading effects, right? To provide a more uniform etch environment, all the way to like a fully dummy, like you have the middle, which is your signal, and then you have two dummies on the side, and then different experiments for the stacking, right? How close or far are the gates in a stack gate, and as well also on the 45, right? And so we'll take a look at what the results here are, but the way people measure this is usually like add metal one, they pull the vapors from the fab and do ring oscillator and leakage measurements. And then that way you can kind of tune the process because you get both a dynamic measurement and also you get the leakage. And then you can put it into your system level modeling to see, okay, is the process good enough for you to be able to do the design? So then you can collect statistics like this and basically say, okay, well, you know, I have 36 chips, 4,000 data points. This is kind of your distribution, right? And then try to fit the process corners that estimate all these variants so that you're somewhere within that boundary, let's say between typical and fast, right? And here you see, I mean, okay, the differences are not super huge, they're 10%. But each one of these at 10%, 5, 6 effects will add in some square root sense, right? So that can still be 20, 30% of your overall delay in the early stages. So you got to be extra careful how you design that. And this, for example, in the ring oscillator frequency. Of course, when you're putting dummies, you can kind of predict this just by looking at layout, right? There's some fringe capacitance here that's happening on both sides. So that's why you're slowed down, right? In addition to kind of how the patterning and etch was happening. And then, you know, for 45, you can kind of look at all of these effects. We're not going to go through necessarily all of them, but people have played with where the position of the poly is over the field oxide around the FET. Should it be in the middle, closer, to really protect the inverter, or to establish a uniform etch pattern across a broader area, right? And so you see those types of things here. This is like a few percent difference, right? For some things, for PMOS, it's a little bit bigger, right? Now, at some point, and different companies started these things at different points in time, but somewhere between 90 and 45 nanometers, people started introducing strain. Transistors were getting slower, or they were getting faster, but not fast enough as people expected, right? So people started trying to engineer different levels of stress in order to shift the conductance planes with respect to the crystallography orientation, right? And if you look at the planar structure, there are two principal components of strain. One is the vertical this is basically gate, right? One is the vertical and another one is the tensile, which stretches, right? Both of these basically improve the mobility. And in NMOS, it's a little bit different than the PMOS. For PMOS, you actually have to, it's kind of interesting. If you look at bulk material, one orientation is really good, let's say 110 with the crystal. But then when you make a transistor, it doesn't get much better. Whereas with 100, you start, you do 110, the transistor doesn't get better, but with strain, it gets a lot better. In 110, from bulk to transistor, it gets better, but with strain, it doesn't get better, right? So you have to be careful what you start from and then how you apply the strain to be able, at the transistor level, not at the material bulk level, to get the gains. And for example, in the NMOS, how do you achieve this? You have the silicon nitride liner. This is the gray stuff, SINX, and that achieves the vertical compressive strain. And then you have these spacers that also pull and create tensile strain. Now, this is all heavily pattern dependent. It's important where the next gate or modern processor, where the next fin sits, right, compared to your gate, meaning what's the pitch here, right? Because that will determine whether the effects are stronger or weaker, right? And so it may seem like the densest design is going to be the fastest, but it may turn out that the densest design is not actually completely achieving the strain target. So you need to kind of depopulate the design to be able to get faster with strain. We'll see that some of those examples next on some of the FinFET stuff. These are some experiments on kind of the longer diffusion, mostly to kind of reduce the leakage and kind of be able to kind of look at the patterning or of where you apply the kind of the longer diffusion here. And of course, the impact of shallow trench isolation, which was kind of introduced here. And this shows you kind of, okay, if you have R1, which is shallow trench, you get essentially a little bit higher frequency because you're able to kind of isolate the transistor. Whereas here you have long stretches of the material. With this isolation, you're able to play with strain a little bit better to be able to kind of control the stress on the transistor. Kind of wanted to give you this example. It's kind of an interesting study that Qualcomm did a few years ago that connects all of these things all the way to the application, not just the processor, but actually what applications are running on top of that processor. And so they build this tool that as they're coming into TSMC and saying, okay, I want to work on the next process with you to build my next chip. The first question comes, okay, what features do you want in the process? We have this 10 different possibilities, and the biggest customers can actually influence the foundry to turn on certain features in the process so they can get the competitive advantage. But how do they know what's good, right? So they build this whole stack tool, and this is really what they're after, okay? They want to know for each type of applications that you're running on, let's say, Snapdragon, they want to know how much battery power they save as they run this blend of applications. That's the level that matters to the end user, right? And so it's not a cycle time, it's not the gate delay, it's basically how much you can run certain stuff on a battery and at what performance level. And so what you want to see is that, okay, well, if I sit in 10 nanometers, this is for different applications. This is kind of how much I'm draining the battery. If I go to 7 nanometers non-optimized, so this is like what the fab said, okay, 7, here's what we offer in 7. They said, okay, that's not really good. I'll show you why. But when you optimize it, you basically get back 20, 30%. And that's then the process you want to invest in and design your thing. But you need to have this like end-to-end view. And so what happened here is if you look at the Elmore delay, and this is something that we've done before, right, in 151, and a little bit of a review in this course. If you look at gate-to-gate delay through a wire, and every transistor has a wire connecting the two gates together, right? Well, what happens in this process, this was N7, is that the interconnect was actually very, very resistive, right? And so if you look at, we're not going to go necessarily into the reasons, but if you look at kind of the interconnect stack, as you're reducing the pitch of the wires, because the interconnect is copper, they have to have the barrier around. If you're reducing the pitch, the barrier is the fixed kind of, or nominally the fixed width. You're trying to shrink it, but you can't really do that much there. So as you're reducing the size of the pitch, basically the percentage of copper inside that area that you etch is less and less, right? Because the barrier is fixed. And what happens with the ohms per square or ohms per micron of length, you basically start increasing more than linearly because there's a fixed portion and you're shrinking the whole thing, right? And that was kind of like an interesting thing that happens here, right? So our wire was at some point in this process way bigger than basically the our transistor, right? So if that's the case, what do? You look at this equation and say, okay, this C pin is really the total gate capacitance as you look at the logic gate, right? So it's like CGN plus CGP basically. And some internal wiring within the standard cell, but that doesn't matter. This is like standard cell to standard cell, right? So this piece doesn't matter, our TRC pin. Our transistor C wire doesn't matter at all also, even though C wire can be big, because our transistor is much smaller compared to our wire, right? But our wire affects, you know, both this term, you can't change it for a certain distance, you need to go. What can you change? Well, you can change C pin. C pin is the strength of your standard cell. How many fins do you have per logic gate? So what they did in this case, they kind of depopulate the cell. So instead of, let's say, 3 fins, they use 2 fins. It's a weaker cell, right? So our transistor, or basically our transistor for the cell is going to go up, but it's kind of small compared to our wire. So actually, when you do all the math and optimization, it turns out that that's a better thing to do. Right? A few other, and so you can see that kind of here as they start doing all sorts of optimizations, like rod optimization helps you shrink this C wire, air spacer around the metal gate helps you shrink C pin, right? And so all of these things help you basically inch by inch go and improve the process. And it shows you here like the unimproved process was basically kind of worse. If you look at actually here, overall delay. This is the initial process, right? It's worse than 10 nanometers. Why the heck do you want to go there, right? But then you turn on these additional features. Let me see if I can move Boris. you turn on these additional features. So from 3 fins to 2 fins, right? You get a little bit back. And then you have this rod optimization. So you reduce the C wire, that helps a bit. And then you have air spacer, you reduce some more. And that's basically your like 30%-ish kind of gain with respect to where you would have been on the other hand, right? So these early views matter quite a bit. Okay. Now diving a little bit even deeper within the transistor, right? So this was kind of like, so far, critical path, the whole design, what happens gate to gate, right? In terms of process features and things like that. Now, what happens within the transistor, right? Interestingly, regardless of what type of device you have, and we're starting from planar devices here that we're showing, and we're going to talk all the way up to the, FinFETs, high-K metal gate structures. Even though the variation mechanisms are different, they kind of manifest themselves in a similar way. And so that's kind of like an interesting irony of nature, if you will. So I'll get to that. This is kind of what is kind of most common source of variation in a transistor, right? You got to control the channel in a planar transistor. You got to dope it, right, appropriately to set the threshold voltage, right, and the leakage levels. Turns out, if you're making this guy smaller and smaller, there's less and less atoms that you can dope into that small region, right, of the channel. And so, okay, you're here at 10 nanometers, you're at like 50-ish atoms or less per that region. Now, the truth is that actually in the most modern technologies, you're actually not doping the channel, right? So that's why we're looking here down to, let's say 32, maybe 45 nanometers, depending on the fab. 28, for example, still planar process. 22 FDSOI, still planar process. Although they do things a little bit differently, but let's say 28 nanometer roughly, right? So still less than 100 atoms. And these fluctuations within the 100 atoms, it's no longer central limit theorem kind of applicable. One atom missing is 1% shift, right? 10 atoms missing is 10% shift, right? So that's a pretty big deal, right? The other thing is that as you start etching, as we talked about, you not only get these width fluctuations, but along the lines, you essentially get this edge roughness, right? And it has all sorts of implications on leakage and power and things like that. How does this all affect the FETs? Well, this is kind of a view on the planar in the FDSOI technology. You plot the sigma of the threshold voltage versus 1/square root of the area, right? The width and the length of the transistor, and you get a line like this. Right? This is kind of called a Pellegrom law from way back when. It turns out, interestingly, it applies to devices, and you could say, okay, it's actually a pretty interesting thing that it applies to planar devices. Planar devices have been forever, right? So there's a certain mechanism, but I'll show you applies actually also to other devices as well, just exactly like that, but from different mechanisms. So another example here is, this is kind of a more detailed FDSOI example where there are two big categories of what can go wrong. One is kind of the short channel sources, and that's the variation in the length and the variation in the thickness of the silicon. In fully depleted SOI, this silicon thickness is like 10 nanometers or 8 nanometers. Look, it's like comparable level to the oxide thickness. Why? Because you want the gate to be able to fully control this as a channel, right? So the thickness is actually really, really small. But then, of course, your conductance depends very heavily on how do you dial that thickness. So these are kind of the short channel variations. And then you have the surface issues, right? What is the variation in your work function that you're going to apply to your gate if you're doing, let's say, metal gate? what is the variation in the thickness of the oxide, right? Also, in this case, the thickness of the body affects, again, these surface sources. What's the variation in the permittivity of the oxide, etc., right? So there's essentially a whole bunch of these. We're not going to go through every equation, but what is interesting is that every single one of these has a square root over W times L, right? Which is pretty interesting for these devices, right? Now, of course, what people do is because it has the same behavior, then you need some other method to distinguish one from the other, right? If they all follow the same kind of trend, you need to engage these other variables in your design of experiments to be able to decompose all these variations when you're designing a process. Now, in kind of more modern transistors, once you have high K metal gate, you're actually adjusting the threshold through the metal gate work function, right? And you tend to have very low doping to no doping kind of channels. But another set of things start mattering in these more scaled structures. And that's basically this is kind of the title, negative bias, temperature, and stability. There's also hot carrier effect and positive bias, temperature, and stability. We'll show it. So negative NBTI affects PFETs. So when you are, because it's a whole type induced mechanism, and happens in, these are like in the stress conditions when the FET has really large negative gate source voltage across it, right? It basically, and elevated temperatures. What happens is that you kind of have these hydrogen silicon bonds at the surface of the oxide and silicon that starts breaking, and then they start basically creating these surface traps and inject these hydrogen-related species into the oxide. So it's kind of like a permanent shift in the threshold that happens because as these temperatures are increasing, these bonds are breaking. Now, that's not the only mechanism. In addition to that, you have hot carrier. In the same condition of operation, you have accelerated carriers that are going through the channel, and they end up getting stuck in that trap or the oxide. So hot carrier has high energy, goes and gets stuck there. And then after a while, it gets released from there, right? So that actually is a statistical effect, right? So charge trapping and hot carrier defect generation. So some of them are going to be systematic, and some of them are going to be random shifts. And so the way this manifests itself is actually as a function of time, right? You keep it running, the more you're running it, the higher likelihood is that some event like this trap event happened. And so your threshold voltage starts degrading. So just maybe I can move this. Okay, that's good. This is kind of an interesting study looking at, we're always looking at kind of the standard deviation over the mean of threshold, right? And in NMOS, you have PBTI. It's kind of a corresponding effect, but mostly has to do with kind of things getting stuck into the oxide stack rather than the interface. So it's a little bit of a weaker effect if you see kind of in comparison with MBTI. These curves are shifted up, right? But you're basically, here, you can't just arbitrarily change W and L because you just have fins. So you can start increasing the number of fins and seeing statistically how things shake out. And of course, you see that as you increase the number of fins, your standard deviation as a function of mean goes down, right? That's this 1 over square root WL kind of thing. The interesting thing is that if you look at this, it's kind of a square root behavior as a function of the threshold. Think of it this way. If I have high threshold, right? One trap has a certain delta VTH, right? So if I have a high threshold, one trap changing something is a small percentage change compared to that high threshold, right? But if I have a very low threshold, that one trap change is now a significant part of my threshold. So the lower my threshold is, the more sensitive I'm gonna get to some number of traps happening with some probability, right? And that's why that curve basically goes up. And then, you know, if you look at the area effects, BTIs, whether it's PBTI or MBTI, they have essentially still that same 1/area dependence on eta. Eta is just a parameter that says, what does one trap do to the threshold, right? The sigma over mean is still a square root of eta. So if this is linear in 1/area, that's just 1/square root overall impact. Right? And so you can see that it kind of affects similarly the logic, the SRAM, etc. And similarly for the hot carrier effect, although it's smaller in magnitude, right? Hot carrier effect is kind of happening when the hot carrier comes in, not when the bonds break and corrupt the interface. Okay, we talked about these, the holes coming in, and that causes another mechanism that looks like this, but it's statistical, and it's called random telegraph signals. And it basically traps a hole in the gate oxide, increases the threshold artificially, and basically, you know, if you have multiple, after some time it releases, you could also have multiple ones, in which case you get the granularity of threshold changes. That's not just a binary shift between the 2 points. These times between a capture and a release are essentially, you know, according to some exponential distribution, right? Of like arrival kind of distributions. And so these could be pretty long. Notice this, the time scale here. It's like seconds. So if you're doing some very sensitive measurement precision experiment, you may be totally dead for a while until it releases, and then you're good for a while. But it's a kind of a statistical thing that you need to watch out for. How do you simulate something that's a second long event, right? You actually have to look at the overall statistics of these things and say, okay, I'm gonna just shield myself against that, assuming it's happening, right? And interestingly, this, you know, if you compare to random dopant fluctuation types effects, this effect overtakes at larger thresholds. It basically +3 sigma, it's kind of a much more dominant effect than random dopant fluctuations. Cool. Here we have some time. Okay. Any questions about variability so far? What we covered? We're going to do a little bit of memory now, as far as I can get. But so far, we've wrapped up the variability section. I don't know if there are any questions, thoughts. Okay. Okay. So here's a little bit kind of a gentle introduction. What is a, you know, a random, let's put this, I don't know, maybe I can, doesn't want to get minimized. Okay. From the architect's standpoint, or even higher up, the user, you know, programmer standpoint, you want to have a memory be just a linear array of addresses, right? Whatever is your word size type address, right? Linear space. Each block holds some data, But this is not practical aspect ratio to realize in hardware. What you really want to do is kind of reshape it so it is some other aspect ratio that balances your delays. And we're going to get to kind of the vanilla memory, for example, that we introduced in 151, where you have and talk a little bit about what things you need to worry about in that aspect ratio. But you're going to have to create some sort of a 2D array just to be able to access these things with some, let's say, moderate wiring, right, distance, even or at the kind of, let's call it microarchitecture or architectural level, right? And that, and then you're going to have some row and column access rather than a linear access here to a particular a piece of data. And this applies both to how the core is organized and if you want to have multiple different banks or cores. So this is kind of the basic memory array people remember from 151 to 51A, right? So what we have here is the cell array, or we call it core. And then you have the word lines that turn on the whole row or the access to the row. And then you have the bit lines that serve either to read or write from these cells, right? And then you have the row decoder that will tell you which one of these word lines turns on. Everything else is down. And then also, if you are writing to a particular set of bits on that word line, you're going to essentially decide that which of these bit lines you activate for that function, right? If you're reading, you could read the whole row, then this mux needs to handle which one of these bit lines get out and in what sequence and where your sense amp sits within the array. Now, if this array, in this array, you have kind of a contention between two different layers, so in terms of the aspect ratio. Does anyone have a clue what these two are? If I want to, let's say, do a read, right? What has to happen? What's the order of events? Yeah, so lift the word line, right? So you have to, you put a row address, you basically decode which one of these. Then this word, whatever is the decoder circuit, has to drive this word line. It's a long wire to drive, right? So what if my core is shaped like this, right? Very long word line, very, very shallow, right? What happens then? My row decoder doesn't have that many outputs, right? So that delay is shorter, but it has to drive this super long wire, right? So that delay is long. What happens to once the word line is on? What happens then if I'm reading? That's the second component or the third component of the delay. Right? Like one is just the row decoder itself. Another one is row decoder driving a long wire. The third one is what? Yes.
You have to recharge the bit line and measure the differential voltage between the two ends of the restaurant.
Yeah, so the cell itself, let's assume the pre-charge happened, kind of hidden, right? The cell itself has to discharge the pre-discharge line, the one that's pulling zero, right? Yeah, so that will be the delay that depends on, okay, size of cell is fixed, for example. What does it depend on, the delay? Yeah, the length of the bit line, right? So if I made the bit line shallow, like short because my word line was long, my delay is long, right? But then all of the delay is in my word line, right? And so that is driving me to kind of optimize the aspect ratio of the array so that all of these delays are basically balanced, right? Okay, so this just give you a little bit of taste, but we're gonna go through these pieces. Now, if you have multiple memory banks, so this is like one bank. How do I organize a core? If you have multiple memory banks, you can have kind of those right next to each other, or again, organized in some fashion where you can much more easily address them. The typical thing is that you start from the LSB and peel off, like even, odd. If you have more, you peel more LSB bits, etc., and go that way. We're going to talk a little bit about the cell itself, and then we're going to do a little bit of a recap of how does SRAM actually work. And then hopefully Apple can then go into kind of more advanced, some of the more advanced techniques. How do you actually drive it for performance and low power? SRAM cells are actually something that I would say is probably the most important circuit in processor technology or system on chip technology. If you look at the sheer number of transistors on any given big compute chip, this is what the number that dominates, right? So designing that one cell and then the array, but even one cell really, really well, it's really the key, right? And what I mean by really well, I mean area density has to be really good because that cell multiplies across a lot. The yield of that process yield of that cell has to be good. So when people go and tune the process, you could see them just running SRAMs. It's like, forget the logic. Just tune the SRAMs to give you the right process balance point. And so here's kind of like, I think this is Bora's sheet, so we can maybe show it here, of kind of plotting. ITRS is basically a roadmap for international roadmap for semiconductors, which kind of plots a prediction how for the technology to scale well, if SRAM is the biggest kind of occupant of the die, it is also the biggest indicator does the process scale well. And this is kind of showing, okay, you know, down to like 50, maybe 20 nanometers, you're kind of following the trend. Are you following the trend now in this region, right? And you see here, there's both how the individual cell scales. There's also how does the array scale, because there are overheads in the array, as we said. There's decoder logic, there is how you route the word lines, the bit lines, all of that stuff. Basically, you need to accommodate even at the cell level. Where do the word lines go? Where do the bit lines go? How many pitches does that occupy, right? And so you see that it is pretty much on track, but it's kind of slowing down a little bit, right? And we'll see some of the reasons are, interestingly, discretization of the transistor pitches and fins, right? These are kind of all the things you kind of have to that we're going to look at, but they're kind of like the critical things for the SRAM. So we're going to look at some basics and trends. The static retention margin, right? It's a cross-coupled inverter circuit, fundamentally, right? So there's some margin as to what disturbance can you put on that cross-coupled node before the inverter flips, right? And so that's called a retention margin. And of course, it will be a function of voltage. As we scale down, these will get smaller, right? And at some point, even the smallest disturbance or leakage can flip it. So then you have the static read and write margins as well, because if you're changing the voltage on the cell, you're kind of changing the relative strength of every transistor. So the one that was supposed to keep the state is getting weaker, perhaps more than the other transistor. So it kind of changes the balance. Then you have the dynamic margins, assist techniques. How do I speed up certain operation? like pre-charging or how they speed up the readout. And then the role of the periphery, right? It's impossible to have no errors in the SRAM array, especially these days where you have like tens of megabytes, hundreds of megabytes, L1, L2, L3, a lot of memory basically placed on the SoC. So you have to have some way of doing error correction. But you have to do it very quickly because these on-chip memories, you want very fast access to them. Maybe from one cycle, L1, to a few cycles, L2, L3, but that's it. You don't want to spend 500 cycles doing error correction coding in a very serious way. And then how does that all scale? So some basics here. This is kind of more of a 151 review, right? We have a workhorse 60 SRAM cell. Okay? You have two NMOS pass gates that provide you word line controlled access to a cross-coupled inverter inside that, and the bit lines both are used to read the information and also write the information into the cell. This, as we will see, is kind of an asymmetric type of inverter, cross-coupled, because the NMOS here is upsized so that the NMOS keeps the state, right? If the state is, let's say, 0 here, this NMOS is actually keeping this state, right? And you can't overwrite this 0 because NMOS is stronger than the pass gate. If you put a 1 here, right? First of all, you're gonna pass not a 1, but 1 minus the threshold voltage. So, so this NMOS is not gonna be able to pull up harder than this NMOS is pulling down. Right? That's the whole intention. But this PMOS here that holds a 1 is weaker than this pull down path. Right, so if you write a 0 on the bit line, you're going to be able to overpower that PMOS and then indirectly flip the other side. And that's kind of the right mechanism into the cell and the reason why you're skewing kind of the inverter inside. Right? You can see that on the layout here. And you know, some rules of thumb here where I was writing like, okay, the ratio of NL to AXL is like 1.5. So you see here, AXL is really the pass gate here, and then you have the NL. This is really basically saying, okay, well, if this was keeping a 0, right, and this was trying to write a 1 to it, because the line was pre-charged, right, that shouldn't overturn the cell, right? So you got to size these things up so that this one is stronger, and that's where this like 1.5 ratio. But that means that this NL transistor is wider in the layout, whereas everything else is the smallest size transistor, right? And it kind of affects how you lay the cell out. And this shows you also kind of how it's done so that the pitches it only occupies basically 2 poly pitches, right? So because all the connections inside the cell are, like especially this cross coupling here is done with mostly poly. So these are kind of some design trends, you know, when you go through something like from 90 nanometer down to 32, you're seeing that the layout of the cell is getting much more regular, right? Because you're trying to compactify the cell into not only small patterns, but also regular patterns. You see that all the polys are the same length. They're all very much kind of properly spaced at minimum pitch. And that gives you kind of that yield uniformity that we talked about earlier in the lecture, where you have to worry about all these loading effects, right? So now you have a sea of things that look identical to each other, right? And so that's where you can do the yield predictions a little bit better. One of the other things is trying to basically look at when the introduction of the FinFET happens. Now you no longer can do like 1 to 1.5, 1 to 1.6. You have finite granularity of the gates. You have 1 fin, 2 fins, 3 fins, right? And that choice is going to affect again your cell, but also this relative sizing. You no longer have a choice for final granularity adjustment, right? So that's actually a challenge. And you know, here you can see kind of how small these cells are, and kind of what the aspect ratio is. This is, for example, roughly 0.1 micron squared in 22. This was kind of a let's say a first FinFET node. Interestingly, the gate right is 45 nanometers. It's not 22. Right? Anyone why the gate? The length will be longer. I mean, you can kind of see that even here, right? A little bit, although not quite. Yeah. But any ideas? Like you can see it here on the FinFET, right? You have a fin, so the length is basically greater than the width. Why is that? What matters in SRAM in addition to speed? I have 10 billion of these on my chip. Leakage, right? Even if one leaks at 10 nanoamps, right? That's 10 watts of leakage, right? On my super low power phone chip, right? So yes, there are ways in which I want to deal with that, and we'll talk about that architecturally. But ultimately, the first knob is how I dial the threshold voltages or the work functions of those transistors, right? And how do I dial kind of the channel length? And also, how do I dial kind of the sizing of the transistors, right? So here, for example, you see that the high density cell, right? It goes with 1:1 ratio. Pass gate, so pull down, pass gate, pull up. Right? You do 1:1, and you're kind of relying on the balance of these two, one being kind of just passing the voltage. So okay, because it's passing the voltage slightly weaker than the pass gate than the pull down, right? So you can still overpower, but you need essentially nominal voltage conditions to be able to do this, and you don't have a lot of leeway in terms of the margin on the retention, but it's the highest density cell that you can use. If you want to go to low voltage cell, right, and be able to have the operation across the low voltage range and better retention, you want to beef up that pull down. Now the granularity is 1 to 2. There's no other choice. So you need to go with 2 fins per pull down, but it costs you some area, right? So it's a kind of a trade-off between area, power. So here again, you have 14 nanometers. They're all kind of in this aspect ratio of length because you're trying to have the minimum number of poly pitches, right, in this direction. And again, the length is always longer than kind of the minimum feature you can design because you're trying to actively control the leakage. So that's an important thing to remember. Same on 10 nanometer. Again, you have people the thing is, you're no longer designing one type of cell. You're designing multiple different types of cells for different operation, let's say applications, right? High density, low voltage, and things like that. Again, it's this FinFET granularity that you have to worry about as you go between the two. These are just some images of that. I want to talk a little bit about this retention stuff, just so people can remember it. We have hold or retention stability. Once the data is written into the cell, what are the mechanisms that this gets overwritten, right? And then there are stabilities when I try to access the cell for a read. Remember, on that 0, there will be a disturbance from the outside pre-charged bit line. Does it hold its ground, right? Or does it flip? And then also the write stability. If the cell is too strong in holding the state, you won't be able to write into it and flip it, right? So you have to be very careful how to do these things. And of course, this kind of contention affects your potentially read access time, right? As we'll touch on as well. So how do you deal with all that? Well, you have to carefully size the ratios of these transistors so that you provide that balance. Okay, this is just with a little bit of drawings, but like as we discussed a little bit earlier, how does this stuff work, right? You have a write, you go, you lift up the word line, right? And then what you're doing is, if the content is already 1, 0 here, right? You can't write a 1 on this side, right? Because this NMOS here is too strong, and it's not letting that 0 go. So what you need to do is write a 0 on the other side, right? And through that, you're overpowering basically this PMOS over here that holds a 1. And so once this pulls down, this one will lift up, because there's going to be a 1 on this bit line. You're going to pass a 1 here, but it's not going to be strong enough to lift it. But once this comes down to 0, both this lifting it up and this now starting to turn will now lift the whole thing. Now, the read is a little bit different. In a sense, you're holding a 1, 0, right? When you open up the word line, there's a 1 here. Okay, 1 here, nothing, right? Now here, there is a 1, but you basically start pulling down because there is a pull down NMOS here, right? So this line is floating, it's a giant capacitor. You're starting to discharge it through this pass gate, a stack of this pass gate and the pass gate and the pull down in this inverter, right? And you have to discharge, this guy has to be strong in pull down so that this intermediate node doesn't get lifted up immediately, because it's kind of like a voltage divider, think about it that way, between the pass gate and this guy. If this gets lifted up immediately by some voltage division from this VDD to ground, then this gate will flip and the whole thing will get overwritten, right? So what you thought was a 0 here will now become a 1, right? And this will become a 0. So that's essentially the read retention. You're trying to read from the cell, but keep the content in that cell, not destroy it. Like in DRAM, you would destroy and have to basically write it back in because you don't have this keeper or pull down device to hold the state while it's being read out. So you just start sharing to the line. But here you do have that active pull down device that's trying to keep the state as you're reading. Okay, we're doing time. Okay, we kind of went through this, but let's see, are we already, yeah, 11. Okay, you have a few more slides as we're gonna post. We just basically went through these waveforms of the basic read and write operation. And hopefully next time, Apple is gonna talk a little bit about more advanced techniques like the underdriving of the lines and things like that, to be able to kind of improve some aspects of the SRAM design. And then Bora will wrap up the SRAM in the, after the break in the lecture. Okay, thank you all.